Hi class, in this lecture here what we want to talk about is the concept of infinite limits. And so what this section is about, so we want to determine infinite limits from the left and from the right. So we're going to revisit this concept of vertical asymptotes a lot. And what we're going to talk about with infinite limits is like how to describe unbounded behavior of a graph. So like as x goes to some value c for some f of x, like how do we say that the graph increases or decreases without bound? And then what we're going to do is we're going to talk about how you find and just quickly sketch vertical asymptotes of a graph. And we did this a lot in the previous lecture as well. And then we also, a lot of this is the same thing from your pre-calculus courses. Okay, so let's consider this graph here. Okay, so f of x is equal to 3 divided by x minus 2. So you can see here that we have a vertical asymptote here, okay, at x is equal to 2. So let's look at the limit as x goes to 2 from above of this function f of x. Now look, as you look at x goes to 2 from above, what happens to the graph? Well, it's just going to shoot up and 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 up forever. Okay, so this is going to means it's going to increase without bounds. So I want to make this very clear. So what we're going to do with infinite limits is we're going to say this limit equals infinity here. Now what this I want to make this clear. When we say equals infinity, what this means is the limit does not exist, okay? Because infinity is not a number, it's a concept, right? It means going on and on forever, increasing without bound, okay? The limit does not exist. We are just describing behavior. So we're just describing the behavior of the function. Okay, so I want to be clear. Whenever we write, the limit as x goes to 2 from above here is equal to infinity, if the limit does not exist, we're just describing the behavior. And so if you look at the limit as x goes to 2 from below of the function f of x, so as I approach 2 from below, okay, my graph is going to shoot down and down and down. As I get closer and closer to negative, or as I get closer and closer to 2 from below, I'm going to go all the way down, I'm going to decrease to negative infinity. Okay, so again, limit does not exist. Just describing behavior. Behavior of the function. And that's the concept we're going to talk about in this class. So when you butt up against a vertical asymptote like this, what we want to do is we want to describe the behavior of the graph by looking at the one-sided limits. Like, are we going up to negative infinity? Are we going up to infinity? Excuse me. Are we shooting down to negative infinity? But just again, rehash. When we say something equals infinity or it equals negative infinity, the limit does not exist. Okay, we're just describing the behavior. So let's look at each of these, okay? So let's analytically find the single value x that is not in the domain. Then let's graphically find the limit if it exists as x approaches c from the left and from the right. So this first one here, okay? F of x is equal to 3 over x minus 4, okay? What we see here is that x cannot be equal to 4, right? And look, if we plug this into our graphing calculator, that's how we're gonna use this here, okay? So we're gonna go y equals 3 divided by x minus 4. And look, you can see the vertical asymptote is at 4. Okay, and so you can see the limit as x goes to 4 from above, it goes to infinity, and as x goes from 4 from below, it goes down to negative infinity. Okay, so limit as x goes to 4 from above of f of x is equal to infinity, and limit as x goes to 4 from below of f of x is equal to negative infinity. All right, now let's look at this one, okay? F of x is equal to 1 over 2 minus x. Well, look, you can see here that x cannot be equal to 2. All right, but so let's plug this into our graphing calculator, right? And let's see what we get. 1 divided by, and then in parentheses, 2 minus x. And look what's happening here, okay? As x goes to 2 from below, it goes to infinity. And as x goes to 2 from above, it goes down to negative infinity. So limit as x goes to 2 from above of f of x we saw was equal to negative infinity. And then as below, limit as x goes to 2 from below, we saw that that was equal to infinity. Now let's look at this one here. Again, you can see here that x cannot be equal to 3. And the squared term is going to make something interesting happen, okay? So when I go 2 divided by, and then in parentheses, x minus 3 squared, okay? Watch what happens. You can see here that as x goes to 3 here, both the limit from below and limit from above are both going towards positive infinity here. Okay, so it's shooting upward. So the limit as x goes to 3 from above is equal to the limit of f of x, is equal to the limit as x goes to 3 from below of f of x. In this case, they're both going to positive infinity here. So in this case, remember, these limits do not exist, but we're just describing their behavior. And then this last one here, the negative sign is going to flip everything, you'll see. So negative 3 over x plus 2 squared. Right, you can see x cannot be equal to negative 2. And if you look at negative 3 divided by, and then in parentheses, x plus 2 squared, you know, it flips it, right? So as you get to negative 2, they're both shooting down towards negative infinity. You can see the one-sided limits. So you can see the limit as x goes to negative 2 from above of f of x is equal to the limit as x goes to negative 2 from below of f of x. And in this case, they're both going down towards negative infinity. And that's just what you're going to have when you butt up against these asymptotes, right? You're gonna increase or decrease without bound. And hopefully you can see that the graphing calculator is like a really great tool for evaluating these, just looking at them real quickly. All right, so a formal definition of a vertical asymptote, we've been talking about them a lot. So if f of x approaches infinity or negative infinity, as x approaches c from the right or left, you're going to see in a little bit, you know, we can have only one-sided limits approach increase or decrease without bound, and you'll see that you only need one side to go up against it, okay? And you're going to have a vertical asymptote. So then this line, x is equal to c, is a vertical asymptote at this graph of f. So just a quick remark, if the graph of f has a vertical asymptote at f of c, then f is not continuous at c, and it's non-removable discontinuity. Okay, it's that non-removable discontinuity. All right, so when you have a function that's described this way, so let's let f and g be continuous on an open interval containing c, okay? As long as, okay, if f of c is not equal to 0, but g of c is equal to 0, okay? And there exists an open interval containing c such that g of x is not equal to 0 for all x not equal to c in the interval, then the graph of this function here, okay, h of x is equal to f of x over g of x, it has a vertical asymptote at x is equal to c. So what this means, okay, when you plug in c in layman terms, okay, what this means is if you have a number at the top and a 0 on the bottom, okay, all right, then asymptote at whatever value you plugged in, x is equal to c. But recall, okay, if you have this 0 over 0, so if you have the value and it plugs in 0 over 0, this indeterminate form, okay, no vertical asymptote. Okay, that's really important. All right, and you're going to see in some of the examples I do that, you know, when you have this 0 over 0, no vertical asymptote. Okay, so let's find the vertical asymptotes of any of these here. Okay, so for this one here, look, you can't have a divide by 0 being 5, right? So if you plug f of 5 in, you would get 2 over 0. So you have a vertical asymptote at x is equal to 5. Now look here. If you have x plus 1, you can see this is going to factor into x plus 1 over x minus 1, right? So notice how you're going to cancel these out. All right, cancel them out. Still the domain. You cannot have negative 1 and 1. All right, but if you plug in negative 1, all right, if you plug in, excuse me, if you plug in 1 into this, okay, like if you plug 1 into this, you're going to get 2 over 0. Okay, so notice how you cancel this out. Okay, so you're canceling out the negative 1 factor. So only a value of x is equal to 1 will create a 1 over 0. Okay, so x is equal to 1 is a vertical asymptote. So what I'm saying here is when you have these rational functions, like simplify it, and then look at the simplified version only for finding the vertical asymptotes. All right, like here, oh my gosh. So remember what I said. You're going to have to find the vertical asymptotes by only looking at the simplified version. So this is going to factor into x plus 3 times x minus 3. Factor out an x. You can see that because they all have an x. And then what you're going to have to do is, this is a 4-term polynomial, you're going to have to factor by grouping. So leave that, make sure you have that x out there. You're going to group the first 2 terms, which is x cubed minus 2x squared. Pull the minus out, so then you're left with 9x minus 18. So look, you factor out an x squared here. You're left with x minus 2. Factor out a 9. You're left with x minus 2. And look, they all have an x minus 2. So don't forget this x. So I have x, factor out an x minus 2. And then look what I'm left with, x squared minus 9. Well, look, x squared minus 9 is going to cancel with that, because that's what x squared minus 9 is. And the simplified version is 1 over x minus 2. So even though you cannot plug in negative 3 or 3, what would happen is if you did, you would get a 0 divided by 0. So what that means then, just looking at this denominator, there's only vertical asymptotes at, well, you can't plug in x is equal to 0. And you can't plug in 2. So if you have these rational functions, simplify them, and then just look at the simplified version for finding the vertical asymptotes. All right, let's look at these transcendental functions here, these natural logs. So we know, if you remember what the natural log of x looks like, right? So if you just look at the natural log of x function, it looks like this. So there's a vertical asymptote only at one side, at x is equal to 0. So look, you have to look, all values have to be greater than 0 here. So if you even just plug this into your graphing calculator. So clear this out. We're going to do the natural log of x plus 3. You can see here, notice how like it stops here. Well, in your graphing calculator, when it stops here, like if I were to zoom in, let me even just move over and get closer to that so you can see. Like what's happening as you get closer to negative 3, like you're butting up against an asymptote there. Okay, so there's a vertical asymptote. Even though there's no graph on the other side, there's a vertical asymptote at x is equal to negative 3 here. So this one is cool, right? So you have to look, and here the squared thing makes things interesting because the graph is only, the domain of this is everything such that x squared minus 4 is greater than 0. So that's going to happen when x values are greater than 2 or x values are less than negative 2. So watch, you'll see that in the graph here. So if I go back to y equals and do the natural log of, let's see, x squared minus 4, and I do a zoom standard, you can see here, remember what I talked about with the asymptotes, you can see at negative 2 and 2, we have these vertical asymptotes. Okay. Let's end by looking at some trig ones here. Okay. So f of x is equal to x divided by sine of x. Well, look, when does sine of x equal 0? Okay. So when does the denominator equal 0? It occurs at every, so it occurs at 0, pi, 2 pi, and so on. So it occurs at when x is equal to n pi, when n is an integer. But here's the thing, when n is 0, you get 0 over 0, right? So remember, you can't have 0 over 0 for vertical asymptote. So let me show you. So y, let me clear this out, x divided by sine of x. You can see here, this is what the graph looks like, right? So at 0, when x is equal to 0, boom, there is no vertical asymptote here, okay? You got it right there. Boom, boom, boom. So when does this thing have vertical asymptotes? When x is equal to n pi, where n is a non-zero integer. Okay, non-zero integer. And look, it's going to be the same thing here, right? So like tangent is sine of x over cosine of x divided by x. So you're looking here, like, if it helps, like where are the asymptotes here of tangent, right? So like tan x has asymptotes at if you were to look at this, right? So it's n pi over 2, okay, where n is an integer. But again, when n is 0, you get 0 over 0, 0 over 0. So y is equal to, if you just clear it, tan of x divided by x. Look, you'll see at 0, boom, definitely not an asymptote right there, okay? So it's the same thing, okay? So this function, f of x, or tan x over x, has vertical asymptotes when x is equal to n pi over 2, again, where n is a non-zero integer. All right, class. I hope this helped. And if you have any questions, let me know, and you'll get a chance to practice this in the coming homeworks.